make this bigger. Okay, so these are my solutions to the first task. As exercises, of course, this is not the correct way to do that, and then it's not necessarily good code. It has been just to show the different function. It's not very well structured. You already had that. This is just to show you how many stuff are present in the headers, which in case you need it from your project, you can pick some fields from that to fill some pandas database, or just to make sure that to test the properties of the images. Like here we have the pixel spacing and the dimension of the image. You can use it to prefill arrays if you need. You have lots of information about the demographics, which, always remember, might not be trustable. And so that's it. They all are codified by an association, so you can directly pick which ones you want to read. Now, this is one of the most important concepts about when you have images and you want to show them. If you just show them without taking care about what's in it, you will not exploit the full amount of information that's present, because I am sure with a grayscale image automatically applies a color map, which might or not might be the best thing that you need for your specific task. So in this case, I ask you to try, let me make it smaller now, to try to, why is that? Okay, now it shows especially bad on this beamer. It's better on the notebook, but what I was about to show you here is that you can use these parameters like impose a gray color map. You can use a vmin and vmax to work within only a color scale. And by the way, it's this pyplot, when you need to, if you make a much bigger image than you have pixel for, it will automatically do some interpolation. And in this case, we can disable that to see how it appears. I'm making a 10-inch by 10-inch image and focusing only on 200 pixels. And you see that if we blow it up like that, we can still perceive the details very well of all these very small features. Then we were asking to see what happens if we add the noise. This image had a minimum of 0 and a maximum of 255. Here I was adding a noise with a standard deviation of 10. In my example, I choose 10. And even if you display a relatively big image, if you take all of these pixels, the 1024 times 1024 image, you don't spot qualitatively that much noise in the image. You might spot something a bit here, but it's not really relevant. Instead, if you zoom in a small area, you see that the strength of the noise starts to be comparable with that of the contrast of the signal. By the way, if you compute the mean square error, you see that it's 100, which, by the way, we added a standard deviation of a signal, a noise with a standard deviation of 10, so this is exactly what you expect from theory. Then I was asking you to try applying some Gaussian filter, which means just removing the highest frequencies. And what I did here, I told you that the Gaussian filter it can be pretty intuitive. It's intuitive what it does. So you set a spatial scale. You see, I'm filtering details smaller than 1 millimeter, half a millimeter. And so you can understand pretty well its impact. And to do that, however, the function from NDI takes the sigma parameter in number of pixels. So here, what you should do when setting it up is to set it in millimeters. So we take from the DICOM header the dimension of the pixel. That's just the help. And then we tried different amount of smoothing expressed in millimeters. So we see here we're doing sigma from the sigma in this pixel list divided by the pixel size. Now, one question that I had in the notes in the markdown was which numbers make sense. The smallest number that makes sense is something comparable to the pixel size. You cannot smooth by less than half a pixel, because if you have a radius and this is how many pixels you're averaging, kind of, so you cannot average something in a diameter of 0.8 pixels. So half a pixel is kind of the minimum, and the maximum has, and indeed you see here I use the small one as 0.1 millimeter with a pixel size of 1.137 or something. And the maximum bound, well, of course, the number of pixels in an image, you cannot smooth more than a quarter of the number of pixels in an image, but that's, of course, will be too much. It depends on if you have, I don't know, like a 4,000 times 4,000 image, it might make sense in some cases to smooth on a radius of 20 pixels, so, which is a diameter of 80, but that's most likely being too much. But there is no really upper scale. I've computed here the metrics that I've previously introduced between the original and the noisy image after the smoothing. And I've applied that also when smoothing the, also when on the original image with the smoothing on top of the noisy image. And okay, so this plot is a bit weird. You can see that for the original image, the highest similarity index is when you have no smoothing at all, of course, while with the noisy, that's smaller. And then there's an optimum somewhere, which will depend on the amount of noise that you have. The less noise you have, the less you can afford to smooth. And here I'm showing the original image, the noisy one with the smoothing, the original with the smoothing and the noisy, and of course in a zoomed in area, because otherwise you don't even spot the noise and not even the smoothing, because you're already compressing many pixels into one. Okay, that was just, this optional task was just what happens when you subtract in an image without noise the original image from the smoothed image. You remain only with the highest frequencies, so you see some boundaries. But if you have even a tiny amount of noise, you will end up blowing this up, and so you will see only the noise excited. The last point concerns what happens if you downsample an image. So you take your 1024 times 1024 image, you downsample it to 256, so you reduce it to the size of 1/4 times 1/4. And then we blow it up again by showing it very big, and you see some artifacts, but it's still decent for what we're seeing here. Instead, if we blow up a very small region, we start to seeing some artifacts. That's one of the concepts that I was telling you. Once you lose some information, you cannot recover them. But also you can see that this is not super bad, so it really means that there is really a lot of information even in smaller images, because you might think of a 256 times 256 as a very small resolution image, while if you use some good upscaling for displaying, there still can be lots of information inside that. Okay, so this is the solution to this part. And the notebook number 2 that I understand you haven't started yet is similar, and it's pretty short. I think that you can finish that in the next 15 minutes. It's about reading a CT image. DICOM files, as I might have told you, quite often are for a volume. Instead, a CT is a volume, not a plane like the X-rays. And more often than not, a volume is encoded as a sequence of files, as a sequence of very small files. So what you need to do here in general is to read all the files and order them. Each file has a slice location field in the DICOM header, because you cannot trust that the file name is correct to tell you the right order. You fill a NumPy matrix array, and then here I'm just asking you to play with displaying that. You will have seen that when you have a volume, you cut it into 3 ways to show the 3 main directions. And I've told you that in many cases in CT and MR, the acquisition is not isotropic, which means that on one direction, generally the direction of the multiple files, the thickness is much higher than the other one, so you might need to plot the correct aspect ratio. And here I'm just telling you to practice playing with the window to see what happens with the different, with highlighting different contrast in CT images. Okay, so that's it. Just let me know if you have any questions about it.